Thank you, Gene and all. I want to tell you a little bit about the survey that we've been working on for a while using background starlight polarimetry in the near infrared to probe the galactic plane. The region we chose to probe covers the intermolecular ring in the northern hemisphere, longitudes 18 to 56, and plus or minus 1 degree of latitude. The idea was to go right into the galactic plane. We wanted to do it at high angular resolution and to reach the high column densities, and that required getting into the near infrared. So this is a survey in the H band. And recently it's been great. Gaia has produced a great number of distances for us, and I'll show you the high degree of correlation we have with those. And so we are into this new paradigm of millions of polarizations, and ours have all been published. I'll point out the survey took 400 nights and over 14 years in the telescope, so I wish my Greek colleagues well. The instrument we used was built for this survey, the Mimir instrument on the 1.8 meter Perkins telescope in Arizona. Has a 10 by 10 arc minute field of view on a 1024 square array. It's a cold instrument, so everything is cryogenic and attended to properly. And in the right, you can see a field of view with polarization vectors, one of the fields of view from Gpips. We also use it in a mosaic mode to go after dark clouds off the galactic plane. Brandon stole my thunder by showing this slide from our recent paper. It is a zoom from kind of the arc minute scale, and you can see the individual stars. The brighter ones have blue vectors, the fainter ones all the way down to yellow vectors, and the high degree of match with Gaia, which is wonderful. In the field view here, so this is one field of view of the instrument, the blue stars are the brightest ones and have the highest polarization signal to noise. If I take those 200 plus stars and average them, then and rotate it into galactic coordinates, that's the blue vector here for this one field. And then its neighboring fields, we can do the same thing. And you can see it looks like it's pretty parallel to the galactic plane. Then you smooth this to 1/2 degree and dump it down here, and you can see the whole survey we've done. And now it looks not quite as uniform as it had. You can clearly see there are waves in the patterns that are present that are pretty large scale. In terms of statistics, we detected unique stars, 14 million of those. We measured 10 million stars for polarization. The brighter ones we call usage flag 1s or UF1s. Those are brighter than 12.5 magnitude and have uncertainty and polarization less than 2%. Those end up with an average sampling of 30 arc seconds in the galactic plane. The metric for that is at 60 per Planck beam. So we have very high spatial sampling. The correlation with 2MASS and GLIMPS are spectacular. GLIMPS in particular, almost every star we looked at, GLIMPS has photometry on. And Gaia had a surprisingly high match of stars with ours. I expected the extinction would have stopped Gaia, but that's not the case. And this is an interesting plot that kind of shocked me. This is Gaia parallax down here in log space, so you can see the distance up here, and then Gaia magnitude from bright to faint. The UF1 stars, the brighter near-infrared stars, occupy these contours. And as we go to fainter infrared stars, it's the UF2s are here, the UF3s are here. And then the stars for which we have Gaia matches to our photometry, but not to our polarimetry, are down here, clearly fainter in Gaia. But the thing is, they're also closer. And so this is counterintuitive. As you go fainter in the near infrared, you're actually looking closer and closer at different stellar populations. So going deeper doesn't actually get you distance. There's too many stars to actually analyze individually. So what we did initially was to look on a field of view basis. So we take all of the stars, the UF1 stars, in a single field of view and look at their distribution functions. So this is a distribution of the d-biased polarization percentage running from a fraction of a percent up to 7 or 8%. And then we use the cumulative distribution function to find the quartile locations of the distribution and characterized this field by its second quartile, its median polarization, in this case 2.3%. We also characterized each of these fields by the log of the number of stars that we saw in UF1. So this one has 179 stars, so its log 10 is 2 1/4. And then we did the same distribution analysis for the position angle histogram here. This is now in galactic position angle. And this, while this looks very Gaussian, and we can still form the same quartiles, the median polarization in this field is 98.5 degrees, where the galactic plane is 90 degrees. We also measured the width in terms of these quartiles in this distribution by comparing the third and the first quartile. And that's kind of related to the dispersion if you had a perfect Gaussian distribution. Oh, in terms of the whole survey, if we take the 3,237 fields, we can do each of those same kind of histogram analyses and produce histograms of the histogram analysis. In particular, here's a distribution of the log of the number of stars in each field. And you can see that the median is 2.41, so that's about 251 high quality stars per field of view that we looked at. The median polarization is about 1.5%. Interestingly enough, the median galactic position angle is at 76.7 degrees. It is not 90 degrees. So at least in Gpips, the galactic plane magnetic field is not along the disk as well as we would hope it to be. And then the width is interesting here. Now, this is all 0 dimension. We can also go 1 dimension and plot those same 4 quantities versus galactic longitude, say. And you see that the log of the number of stars actually increases as we go to lower longitudes. The polarization kind of wanders around. The position angle wanders around with kind of a 2-degree period or something. And then the width does crazy things. So what's going on? If we go to 2 dimensions now, and so now we're mapping longitude and latitude from 18 degrees, and this wraps around until we get to 56 degrees, and this is the full plus and minus 1 degree. Each of these little squares represents one of our fields of view that we've measured. And now we're plotting here the median polarization in each field. And you can see it gets up to as much as 3%, and it runs a little higher along the midplane.
3 minutes.
We could do this for all of these quantities. So log 10, we can see the presence of the bulge showing up. In the dBGPA, which is the width, we find regions where the width is actually lower, and I've chosen red to represent lower here. And then the GPA map is kind of goofy. There's patches, there's zones that are uniform, but they're 45 degrees or 30 degrees off of what we would expect. Did we find correlations in those 4 quantities? The answer is mostly no. This is a standard corner plot, taking those quantities 2 at a time. The one exception is actually the one we've talked about before, which is the polarization versus the dispersion. That shows an inverse relation, high polarization and low dispersion. Where do those occur? We selected the 6% of the Gpips fields of view that had the highest polarizations and the lowest widths in their distributions and plotted them here in latitude versus longitude and galactic position angle versus longitude, and then found things that look like they were structures. Found 10 of those things. They have average sizes less than 1/2 degree. They don't correlate with known star formation regions. And so the question is, are these just regions where the plane of sky, where the magnetic field is perfectly in the plane of sky, or are they strong magnetic field regions? Okay, so Gpips is, I hope, a new enabler of magnetic field studies at high angular sampling and up to moderate extinctions. All the data were released last summer. You can get them from URSA by just Googling Gpips URSA. You can get them from the CDS with Vizier. You can go to our website, and there's a QR code that'll get you there. We have a unique star catalog. We have a different set of star catalogs that are based on the individual fields of view. We have co-added images with and without overlays, everything you could possibly want. What have we found so far? The stars that we've measured span wide ranges of brightness, extinction, distances, and stellar types. The galactic disk magnetic field is not so simple. In the mean, it is 13 degrees off of the 90 degrees expected. In 1D and 2D, there are these 1 to 2 degree angular size things that show coherence, but need to be explained. We see the anti-correlation of P versus PA dispersion that's been talked about. The regions that have low polarization and high dispersion are fairly ubiquitous in LB space, but the ones that have high polarization and low dispersion are rare, they're clustered, and they're not correlated with star formation. So what are those regions? And then the high match rate of the UF1 stars with Gaia, at least DR2 even, bodes really well for developing the 3D map that Brendan and others have talked about. We're really looking forward to DR4. And then I'll just leave you with my thanks and a little bit of eye candy here. This is an infrared dark cloud that we're studying, which is Heraklion. The blue vectors represent just 9 of the Gpips fields in a 3x3 matrix. We've selected them not to be UF1 stars, but in other directions or in other ways. And then the red are K-band, a little bit longer for one field of view. And what's the opaque thing in the middle there is the infrared dark cloud. And in addition to the fact that we can get very, very close to the infrared dark cloud, AVs up to 50 or so, you can see waves and patterns in the blue background that are really crying out for analysis. So thank you for your time.